Thanks for the introduction. And yeah, so as Edita said, the focus of my talk is going to be different from Tibor's, and I'm going to be focusing on using quantum LDPC codes to try and construct scalable quantum circuits. So in other words, for fault-tolerant quantum computation. So to start at the top, like why are we building quantum computers? One killer app is quantum chemistry. And if you were to look at this recent paper from Microsoft to see how big our circuits have to be and what the numbers are going to look like, ballpark estimates are saying that your qubits have to be reliable in that only 1 in like 10 to the 17 of these qubits are allowed to fail if you want your simulation, your chemistry simulation, to have an accuracy of like 0.99 or 0.999. Okay. But unfortunately, our qubits are error prone, and what this means is that so rough numbers are like 1 in 10 to the 4 gates fail today, and what it means is that if you were to input these circuits raw into a circuit, these qubits, because they're error prone, it could cause this sort of avalanche effect where errors then spread to every other qubit, and your entire simulation is useless. So in the early days of quantum computing, this was, of course, a conundrum until people figured out how to deal with it. And the way to deal with it is to use the imperfect qubits that you've got to simulate an ideal qubit. So this big check mark here is a good qubit. And if you look under the hood, what you see is the following thing. So again, we're starting with the same sort of setup that we did before. And one of our qubits has an error on it. And what quantum error correction, the idea is, the mantra is that you're going to be trying to correct errors faster than they can occur. So this entails performing joint sets of measurements on qubits. And when you do so, these measurements might detect errors. So this joint measurement at the very top in this little cartoon has detected the error up top. And then the circuit proceeds, and then conditioned on having detected this error, get corrected, and now you have a clean set of qubits. Okay, so that's the idea. And what we're trying to measure here is this function p sub q for the error correcting code q, and it is a function of many things. It's a function of the physical error rate, the rate at which your gates and qubits are failing. It's a function of the total number of qubits that you've got in your system. It's a function of the number of good qubits that you're trying to simulate. And potentially other aspects of your construction. We would like to focus on a case where we think of it as a function of n with these other parameters fixed. And the crown jewels of the theory of fault tolerance, they're called the threshold theorems. And they say something super counterintuitive. They say that below a threshold, if p phys was not too high, then you can suppress errors arbitrarily by increasing n. This is counterintuitive because you're increasing the size of the system, you're introducing more points of failure. But even while doing so, the system is becoming more robust, and you can make the logical failure rate arbitrarily small. So thinking back to our chemistry simulations, we then have, say, for a certain target logical error rate, it guarantees that you can scale your system size large enough such that this is possible. And just a minor aside, what do I mean by errors? In these sorts of proofs that we're seeing in these threshold theorems, it's not just simple IID errors. We allow for like fairly complicated error models where things can fail in a correlated fashion, errors can spread within your circuits, all sorts of funky things can happen. And even in the face of this sort of general error models, we can guarantee that a threshold exists. Okay. So this is the space within which we're working. So now with this sort of cartoon in mind, to build on this and introduce some notation, once we have a code, right, this is specified by some joint sets of measurements, and this corresponds to some syndrome extraction circuit. This is the workhorse of any computation, and what it is it's a circuit that takes these commuting set of measurements that specify your code and tells you how to do this in circuit form. This circuit is not unique, but you can try and construct one such circuit. And the way that you try and gauge whether or not this circuit is useful is by using some metrics. The most important one, or an important one, is the width of the circuit. So this is one, the non-negotiable. The non-negotiable is the data qubits that you started with, right? So you've got some encoded state psi, it's got some errors, you've got some in silico qubits prepared in some big state, and it goes through the circuit and you detect some errors. So this is some giant unitary circuit followed by some set of measurements. And the width of the circuit is the non-negotiable. So, I mean, you can't throw away the data that you've been given. But in addition, you're also using some n silico qubits. So the width of the circuit is the total number of qubits that you're going to need to guarantee fault tolerance. And 2 is also the depth of the circuit. The depth of the circuit is the number of time steps that you're running this little syndrome extraction circuit. This thing, as I said, is the workhorse of any quantum computation. And how it's going to work is if you want to perform gates in your circuit, you're going to have to interleave this error correction protocol with between your actual gates that you're performing. Okay, so I'm not going to be talking about that part of the computation. I'm not going to think about how error correction works in the context of algorithms. I'm going to focus simply on this little workhorse and how we perform syndrome extraction. That's all I'm thinking about today. And finally, we have the decoding algorithm. So once it's gone through your circuit, you have some large classical output. You have some bit strings, and you'd like to say, given this bit string, I'd like to go back and deduce what exactly the error was. And these are the things that you're paying. And you'd like to minimize the cost of constructing a syndrome extraction circuit. On the other hand, what are you getting in return? One, as I said, quantum error correcting code is a way to simulate the qubits, so you're able to simulate some K qubits. And 2, you'd like to be able to tolerate some number of errors, and that is called the distance of your error correcting code. It's a sort of worst case metric. It says many things have to go wrong before your encoded information is entirely corrupted beyond recovery. And you might think, well, that sounds a little bit like overkill. We don't have this sort of worst case setting in nature or in my circuit. Errors are only occurring in a stochastic manner, and often what we find is that errors are suppressed when they are occurring probabilistically. Errors are suppressed exponentially in this distance. So that's how it plays a role in understanding stochastic errors. Okay. Now, this is the payoff. You'd like to minimize your cost and maximize your payoff. And rather than think of these two things separately, an alternative is to use what's called the space overhead. And what this is the ratio of the width of the circuit to the total number of qubits that you want to simulate in your algorithm. Okay? And this has been identified as a bottleneck to scalability. So the thing that we'd like to try and do is minimize the total number of qubits that we're using, or in other words, we'd like to minimize the space overhead of our circuit. So let's start with everyone's favorite error correcting code, namely the surface code. This is a code that's geometrically very pretty. It's constructed on a 2D square lattice, and the protagonists of the story are the vertices of this lattice and the faces of this lattice. So each of these faces, there are many variants of the surface code. The one that I picked here because I found it pretty pictures online. How it works is you perform measurements of qubits. Every face now corresponds to it specifies one of these joint measurements, and you perform a joint measurement of the two qubits on this side in the x spaces and on that side in the z. Okay, and if you go across your code, you can convince yourself that these do indeed specify some commuting set of measurements. Okay, so this is how my code has been specified. Alternatively, I could give for you the syndrome extraction circuit, and how is this going to work? I need to tell you how to measure these operators. I could have an in silico qubit initialized corresponding to every face. This direction corresponds to time. The white dot corresponds to my data qubits. And what happens is, as time proceeds, I perform entangling gates from this in silico qubit to all of my data qubits and complete with a measurement. Okay, so and there's a way for you to do this in lockstep so that you can perform all of these measurements in parallel. and the total depth of the circuit is 6. So you can measure all of your syndromes in constant depth. So you're not using too much depth overhead. And how much is the total space overhead? Well, it's the number of qubits that you begin with, is L squared. And corresponding to every face, you have 1 ancilla qubit, so that's also L squared. So roughly the space overhead is L squared divided by 1. Why is this code great? Well, for many reasons. One, it's very simple, right? I can arrange this on a 2D squared lattice, what could be simpler. And what this guarantees is that the errors can be suppressed exponentially in the side length of this lattice. Okay, so it's an L by L lattice, and errors are going to be suppressed exponentially. C of S is some constant that depends on other details of this construction. And what this means is that there exists some threshold point below which this like counterintuitive thing happens. The thing that fault tolerance guarantees will happen, where as you increase your system size, so the numbers here indicate the size of your lattice, side length of your lattice, and you can see that as for a fixed error rate, if I fix the physical failure rate of my gates, as I increase my code size, the probability of logical failure decreases. On the other hand, if I'm above the threshold for a fixed size, as I increase my code size, things start to get worse. So this threshold is this critical point that's telling you where this qualitative difference starts to occur. And for the surface code, it's quite high. In fact, I think it's the highest among known codes. And so, in addition to its simplicity, it also performs really well. It has a very high threshold, and this makes it a very good blueprint for constructing scalable quantum circuits. And so if we like dig deeper and ask ourselves, why is it that it's performing so well? Well, one of the reasons is that within the syndrome extracting circuit, every qubit only talks to a limited number of other qubits. By talk, I mean they're involved in some 2-qubit entanglement. And in this particular setting, you can see that every qubit, whether it's a data qubit or an ancilla qubit, in the circuit, every qubit only talks to 4 other qubits. And what this means is that you're limiting the ways in which errors can spread. If every qubit was talking to a number of qubits that grows with the system size, then there's more ways that errors can spread. Entangling gates are spreading errors from one qubit to another. There's more ways errors can spread. And by limiting this, we find that our syndrome extraction circuits perform well, and we have a high threshold. Unfortunately, what this code, the gift and curse of the surface code, the downside of using the surface code is that it only encodes a single qubit, regardless of how big you make your lattice. Okay, so if you were to look at this overhead factor, this is then going to grow with the number of qubits that you want to stimulate. Okay, this is going to grow in an unbounded manner. So if the name of the game is to make our circuit constructions efficient, if it's to ask what is the best way for us to construct scalable quantum circuits, what is the nicest way we can pack things into a small space, this is saying that there's like some fundamental limitations as to how good this can get. Right? So ideally, what I might ask for is that, hey, I'm using L squared qubits. Why don't you allow me to encode, a third of them, right? And this is not directly possible with the surface code. And second, the error suppression is also suboptimal, right? So before I said that the error is exponential in the side length, but really, again, I'm using L squared qubits. The distance could also be proportional to the number of qubits that I'm using. Why isn't that also falling as exponential L squared rather than simply exponential L? So, yeah, so why won't we make a better code? And the answer is, so such codes do exist, and these are what LDPC codes are. So we keep the parts of the surface codes that work and dispense with what doesn't. And what is the part that we find that we like? It's that every qubit only talks to a limited number of other qubits. So that is what an LDPC code is, except now we're dispensing with geometry. We're giving up on, we're not asking that everything be arranged in a square lattice, and I'll return to this in a sec. All we're asking is that the syndrome extraction circuit is constructed such that every qubit talks to a constant number of other qubits. And in particular, what we've shown in 2 beautiful papers, first by Kovalev and Piatko, and then later by Daniel Pakistan, is that you can use these for constructing efficient quantum memories, namely simply input and output of your quantum information. And then later got to show that you could use this also for performing quantum computation. But the idea is that if you've got good codes, namely if K and D are scaling in proportion to the total number of physical qubits that you're using, then you have exponential error suppression, not for one qubit at a time, but for all of your logic qubits. And this is a massive qualitative difference, and this is part of why LDPC codes are so appealing, at least in theory. Okay, how does this translate to this this metric that we were interested in using? We asked for the space overhead, namely your circuit, the width of your circuit divided by the total number of circuit qubits that you want to simulate. And it turns out that if you were to use good LDPC codes, this number becomes a constant. To achieve a fixed target logical error rate epsilon, the space overhead is a constant. So that's the advertisement for LDPC. Okay, so if it's all that good, why isn't it already here? And that's what I'm going to be spending the rest of this talk talking about. So all of these results exist in asymptotically. They hold true when k goes to infinity, n goes to infinity. But if we ask ourselves, for finite block lengths, I've only got so many qubits to spare. I don't have infinite qubits. What is all this theory by me? Unclear. So let's peel back. We're going to try and understand some of the assumptions that Gottsman and earlier Kohlmann and Jakob made in their papers, and ask, what are the assumptions that they're making, and what is it that we have available today in our labs that we can actually do. And the first one is that when Daniel had written this paper, it was unclear whether such codes even exist. And since then, there's been a lot of progress. You may or may not have heard of this, but a few years ago, there was so this problem of knowing whether or not good LDPC codes exist lay dormant for 20 years. And then after, in COVID summer, it felt like every 2 weeks after COVID summer, there was a new breakthrough, right? And a series of breakthroughs ultimately resulted in these 3 papers. They're all variants, very closely related papers, and they showed that this mythical creature, this unicorn, exists, that these good LDPC codes exist. So that's part of one of the assumptions that was baked into Gottsman's paper that is now resolved. And 2, yet another assumption that Daniel made in his paper is that you can perform 2-qubit gates between arbitrary qubits. So you've got your code, you spread your qubits in a, say, L by L lattice, and it assumes that you can perform 2-qubit gates, entangling gates between arbitrary pair of qubits, no matter how far apart they are. And furthermore, that you can do them in parallel. Okay, so these are very strong assumptions, and they don't necessarily hold in all architectures. And this is something that I'm going to spend some time getting back and talking more about. So the first part of my talk is going to be NOVA results. This is work done together with Noiten Westman, who is currently a PhD student with Stephen Bartlett at Sydney. Okay, so as we said, one of the things that makes the surface code so appealing is locality, right? So you can arrange this in a 2D grid, and all of your 2-qubit gates are just between nearest neighbor qubits. And when we ask this question, why can't I construct better codes? There's some fundamental physics involved here. There's this beautiful paper by Rakovszky and Hall from 2009 that's basically trying to generalize the results here have shaped the past 3 years, a lot of my research over the past 3 years. What does this paper say? It says that if you have a surface code with only nearest neighbor connectivity, then you're in trouble. K, remember, is the number of qubits that you can encode in your code, and D is the distance. This is the number of errors you can protect against. And they're saying there's a very sharp trade-off between K and D. If one increases, the other has to decrease very sharply. This bound is multiplicative. And in particular, if you were to plug in the parameters of the surface code, so this is L squared, D is L, K is 1, up to constant factors, you've saturated this bound. So what they're telling you is that if you were restricted to nearest neighbor connectivity, there's not much more you can do. So we'd like to ask, how does this extend to arbitrary codes, right? So they're saying if locality, then bad stuff happens. But we would like to ask the question, look, I have a code that I'd like to build. What's it going to take? Okay. So it turns out that there are some very useful properties of graphs that are able to characterize or generalize this Ravi-Poulan for Hall-bound to arbitrary settings. And it's the tool that we're using that we repeatedly return to is something called a separation profile. So first, let me tell you what our graph separator is. So here's some graph. I've got some nodes, and these yellow lines represent edges. And the graph separator is this set of vertices. When I remove it, it partitions my graphs. It cleaves my graph into two roughly equal sized pieces. And the profile here that I'm referring to is not merely for the entire graph. It may be that like one portion of my graph is very well connected and another portion is very poorly connected. And I'd like to be able to zoom in on any portion and guarantee that it's well connected. And the way that it works is that if I would consider some portion, an arbitrary portion G prime within my big graph G, and it has the size of R, then I'd like to ask, what's the worst way it could be connected? And this is quantified by the graph separator. It's a measure of the connectivity of your graph. And in this case, in the 2D grid graph, you can do just by staring at it, because it's square root R by square root R grid. If I were to remove this column of vertices from the middle, then I split it into two roughly equal pieces. And so in this sort of like uniform 3D case, the graph separator scales as the square root of the little chunk that you can see. And it turns out that this quantity is really what they're using here implicitly without actually saying it. And you can generalize their result and phrase this in terms of graph separators. And it says that good codes are going to require large separators. In other words, good codes are going to be very tightly connected, and it's going to be difficult to break them into two pieces. And what does this imply for implementations? Again, I'd like to ask, what does this mean for my circuit? And it says that if I want to implement these good codes, right, I've got an L by L grid where I've laid out my qubits, square root n is now proportional to L. And in this setting, I'm going to have L squared edges. So basically a constant fraction of my qubits, say 10%. 10% of my qubits are going to be connected to qubits all the way on the other side of the lattice. These omegas just mean that it's at least proportional to. So just substitute every omega with a greater than or equal to sign if you haven't seen it. But basically that's the catch. So when we started working on this, some folks working on Eric Harkin had also asked us, we've already constructed these good surface codes. Is it possible that we can now like leapfrog, get to a good code merely by connecting corners, right? Just connect this corner and that corner, that corner and that corner. You've already violated the assumptions that are baked into the Ravi-Poulan Hall-bound because that's it, only locality. And now you've added not too many non-local connections. You've only added a constant number. Is that sufficient? And unfortunately, this result says no. It's not merely that you have non-local edges, but you have to have a lot. Okay? And what does this imply for Gottesman's result? I'll go back and ask, this is one of those things that was baked in. If you have two qubits that are far apart that need to talk to each other, right? And I need to perform a 2-qubit gate, but I only have nearest neighbor C naughts. How am I going to do this? Well, I only have basically one trick. I can swap qubits over, perform the C naught, and then swap back. But if they have to move a distance of L, then this implies a minimum time that I need to perform my circuit. If I have arbitrary connectivity, 3 minutes. Oh boy. All right, let me speed up. I just want to say that so in contrast to these normal results, I can also have a Go result. And the idea is that because each of these qubits is failing with a constant probability, I can encode each of the qubits in my LDPC code into a surface code. And by doing so, the surface code is going to suppress errors exponentially in L, whereas each of my the total number of units that I'm moving from one end to the other, so square root n is proportional to L, remember. This is falling exponentially in little l, that is growing polynomially in n, so exponential versus polynomial. It turns out that you can overcome this, this problem by using a little surface code, by encoding all of your qubits in your LDPC code in a little surface code of size log n by log n, and you can encode a growing number of qubits. And although this code is no longer technically LDPC, you can get away with using only local measurements. I guess I missed a slide. So this is work with Chris Hatton and okay, so we also presented a way for you to implement this code in a bilayer architecture, and this uses only nearest neighbor connectivity. Okay, so that's the payoff. If you're willing to accept this growing depth, then you have an explicit arrangement. So this is no longer merely a no-go result. We have an explicit construction for you that can basically saturate these bounds, and it's still constant overhead, or almost constant overhead. And we can also tell you the depth of the circuit. And for seeing what might be available in the near term, you might have swap gates of range R that are scaling with the system size, maybe not all connectivity, but something that grows with system size that can help you reduce the total depth of your circuit. Okay? And finally, the last advertisement is that this code actually has a threshold. So below this threshold, the logical failure rate is not falling exponentially in n, but n over some log n. And this log n penalty is what you're paying for being able to implement everything locally. There's no way to get around that. But you can compare this with the surface code where you're only suppressing errors as square root n. So there's a massive difference. So this is that was in asymptopia. I also have some concrete numbers to ask, asymptotically something happens, but like in real life, where does this crossover manifest? For the interest of time, I can skip this. There's also a bunch of things that we need to do to be able to realize these codes in practice. So we now have like explicit syndrome extraction circuits, but we still need to think about how to implement fault-tolerant gates, efficient decoding algorithms, and how you might tailor your code to a specific architecture. So with that, let me leave my conclusion slide up and
so since you had to get cut off, so the punchline of the second part was what?
That you do have an explicit, so on the one hand, we have these lower bounds that are telling you can't do better than this. And on the other hand, we have an explicit construction that says that you can basically match it by using the simplest trick in the book, just concatenate to the surface code. And the surface code is basically going to protect your qubit long enough so that you can, if you squint, you don't know that it's a concatenated code, it's still an LDPC code. So as far as you're concerned, the outer LDPC code is performing well enough that you can pretend that it's an LDPC code. But on the inside, there's this little surface code patch that's growing steadily, but it's not growing too fast. So without incurring too much space overhead, you're able to realize an LDPC.
We have 5 minutes for questions before we move on to the next.
So you skipped over, and you emphasized at the beginning that this was all asymptopia.
Yeah.
And you proved these general scaling results.
Yeah.
What does it mean for what could be done?
Yeah.
Non-asymptopia.
Right. So one thing that's promising is that if we compare, so you might ask, look, I'm using all the same resources to do something hyper complicated. I'm like swapping stuff. Why not just use the surface code? And because you have this exponential error suppression for all of your qubits as opposed to like one at a time, what we're plotting here is like physical error rate versus logical failure rate. And at some point, you're going to see a crossover. This LDPC code concatenated with the surface code is going to outperform your surface code, merely using surface code. And our first preliminary results are promising because this crossover seems to happen at like reasonable error rates of like roughly 10 to the minus 3, as opposed to happening at like 10 to the minus 50 or something absurd. So for first pass, that's pretty good, but there's also a lot of pessimistic assumptions that are baked into getting these sorts of plots. And we think that things are only going to get better. The reason that this isn't optimal is because of the code size looks more like a telephone number. And it's unlikely that you're ever going to be able to implement that. But this is also because of these pessimistic assumptions that we use to get to these plots. And I'm very confident that it's going to be a whole lot better if you're to run actual numerics without having to make some research.
But Tibor starts sets up that one more question.
Yeah.
So if LDPC codes are not realized, how does it impact division by people?
Right. Yeah. So you still have like long-range connectivity to overcome, but now the surface code, you're now implementing logical gates on the surface code. So by treating your surface code patches as your qubits for your LDPC, you're now implementing logical swap gates. And that's then helping you implement the syndrome extraction circuit encoding. So that's how you get around it. So rather than now using only physical gates, you're using logical gates for the surface. And the penalty that you incur, of course, is that the depth of the thing is still growing, that you can't overcome. But because of this like exponential gain for the LDPC code, you still win out.
Okay, let's thank Ani again and.
All right, yeah, so as Vedika said at the beginning, my talk will be also on LDPC codes, but from a more physics perspective. And that means both kind of using ideas from physics to say things about LDPC codes. But it also means kind of using LDPC codes to motivate questions that are more physical in nature. So I'll start with an introduction, which will overlap a bit with what Ani said, so maybe I can go quickly. So you're imagining some code, some physical system where you're encoding some information, and you often characterize it with these three numbers. There's a number of physical qubits n, there's a number of encoded qubits k, and there's some code distance, the smallest error that I cannot detect, which is d. And we want to make k and d as big as possible for a given n. And in these LDPC codes, we have this constraint that we want every bit or qubit to go to a finite number of bits or qubits. And as Ani said, that's useful for limiting alpha error spread. But from a physics perspective, it's also a very reasonable constraint. It means there is some notion of locality that's built into our system. And in physics, usually one thing to be local. And if I want to think of this as physics, I can also translate it as the system size is the number of bits. K, the number of logical encoded bits, is something like the number of ground states in the system. If I try to use some physical system to do this encoding and to do some low energy ground state subspace that encodes the information, and the code distance is kind of the number of bits I have to split for actor to go from one ground state to another. And I'll be going back and forth between thinking of them as codes and as physical systems throughout the talk. So two useful examples to have in mind that I will come back to later. For a classical code, just the classicalizing model that probably everyone has seen. So I have some bits arranged in some lattice in d dimensions, and I have nearest neighbor interactions between the spins, ferromagnetic. And this is a system which I can think of as a code. There are L squared many bits or spins, and they encode one bit of information in the two ground states, which are all spin polarized up or down. And this is a large code distance because I have to flip every single state to go from one ground state to another. And for a quantum example, there's a toric code, which is more or less the same thing as the surface code that Ani described. So I have qubits now assigned to the edges of a square lattice, and my system is defined by two kinds of interactions, one for the vertex, one for each vertex and one for each plaquette, which all commute with each other. And I end up encoding 2 bits of information, which is kind of encoded in loops that wind around the torus in some non-trivial things. And because they have to wind around the whole torus, the code distance will be linear in the linear side of the system. Okay, so one thing to notice about both of these examples is that I had a large code distance that somehow grows with the size of the whole system, but I only encoded a finite number of bits. And as Ani said, in fact, this kind of trade-off is generated for things that are local in some Euclidean lattice. That I cannot, if I try to make the code distance big, I have to at some point make the number of encoded bits smaller or the other way around. So there are some nice general bounds, both for classical and quantum systems. And as I said, ideally, we would like to overcome these bounds. We really want to have what people call good codes, where K and D both scale linearly with the number of bits. So the optimal possible scaling. Encode as much information as possible, as robustly as possible. And to do that, then we have to use some connectivity, some graph, which is not a Euclidean lattice, but something much more highly connected, in particular, things called expander graphs. And the basic intuition of an expander graph is some sort of graph, has some vertices and edges, that they're connected in such a way that if I take some subset of vertices and look at its boundary, the vertices that are not in that set are connected to it, the size of the boundary is proportional to the volume of the inside. So this is something that really I cannot get in Euclidean space, where surface is always smaller than volume. But if I allow to draw graphs of arbitrary graphs with a finite connectivity, I can get these things very easily. And in fact, I need something like this, as I said, to get good codes. And I want this to be true for basically any subset, at least if they are smaller than some finite fraction of the whole graph. And it's been known for a long time that if you allow yourself to construct LDPC codes on expander graphs, you can relatively easily get good classical codes which satisfy both K and D being linear in N. You can just basically draw things randomly and it will work with a high probability. But for quantum codes, it's been unknown for a long time. And as you heard, it's only in the last couple of years that a number of breakthroughs will lead to a point where we now have constructions for these codes. Okay, so that's one piece of motivation, that we now have these constructions of good quantum codes. We would like to understand them better, and we also understand them from a more physical perspective. But there's another piece of motivation also coming from error correcting codes, but from the classical side. So there have also been some recent breakthroughs about classical error correcting codes. As I said, it's been known for a long time that you can get these good classical codes which have an optimal scaling of number of encoded bits and for distance. But now you can get greedy and you might want your code to have even better properties. And one property that you might want is this property called local testability, which is that, let's say someone hands you some arrangement of bits, and they tell you, this is a code word, this is one of my ground states or my encoded words, and I'm trying to figure out, are they lying or not? Is this actually a code word or not? But I don't want to go through the whole thing and check it everywhere. I want to be able to kind of tell this by just looking at the configuration locally somewhere. I pick out a few bits randomly, I look at them, and I want to decide with some good probability whether it is actually one of my code words or not. And in particular, the probability that's kind of proportional to how many bits have been flipped compared to the code word. And this is also can be thought of in more physical terms. So if I think of this as some physical model where the encoded bits are the ground states of the system, then the question I'm asking is, if I start with the ground state and I start flipping spins, how quickly does the energy of that configuration grow? And what I want is something where no matter how I do this flip, energy goes linearly with the number of flips I've done. And it's a pretty strong requirement. And to see that, you could consider this to the Ising model. If I was clever, I could take the ground state, all spins pointing up, and flip spins in some big connected block. And I get something where I'm very far from a ground state that figment spins, but the energy cost that I incur is actually pretty small. It's on the boundary of this. It grows much more slowly rather than linearly with the number of spins. So this local testability, if I really want a linearly growing energy cost, no matter how clever the actually the spin, is actually a pretty strong constraint, which actually I can also only really achieve if I work on some expander graph rather than on a Euclidean lattice. Okay, and this is also something that has only been realized in the last couple of years. And interestingly, the actual explicit constructions of realizing it are very similar, or often the exact same constructions that have been used to create these good quantum LDPC codes. So there have been kind of these two parallel strands in the last few years. but they use very similar mathematical tools to get, on the one hand, quantum codes with optimal distance, and on the other hand, these classical codes where with this optimal scaling of kind of energy barriers. Like one way to think about this is, how big is the energy barrier between two graph states in this classical model? This is kind of the optimal scale. Okay, so these are the pieces of motivation that sort of got us started and trying to understand these features in a physical way and also their connections. So one thing to emphasize here is this is kind of an interesting new regime for physics in general, thinking about models which have a notion of locality. So you could use lots of tools and ideas that you're used to from physics, but you also relax your notion of locality in a way that allows for new things to happen. And all of these examples that people in computer science figured out tell you that new things do happen. So it's worth thinking about it. But if you want to think of these as more physical systems or than codes, there are other sets of questions you would ask, for example, about perturbations of these physical models. Can you think of these as phases of matter in these combinated graphs? What kind of phase transitions you get between them and so on. And so what we are doing is kind of making some steps in this direction by developing an appropriate language to think about these, or generalizing ideas that work well in more usual cases. In particular, what I will show is that you can think of all of these quantum LDPC codes, even those that live on very complicated geometries, as some appropriate version of what in physics is called the Z2 gauge theory. So the Z2 gauge theory, I'll review it in a second, but it's a very well studied kind of physical system that shows up in many contexts, and there are kind of useful parallels here that can also suggest kind of ways of perturbing around these codes and asking about their stability. And another thing that comes out of this is a kind of duality between classical and quantum systems, as I will discuss. So you can actually think about the phase diagrams of the quantum system with the classical systems and relate those to each other, and also match the various properties between them. And in particular, this perspective kind of sheds light on why similar constructions give you these locally testable classical codes and the good quantum codes. As I will argue, under this duality, kind of the domain walls of the classical system that you get by flipping spins relate to the logical operators of the quantum code. So there is some relationship between how quickly the energy goes as you start flipping spins and how big is the code distance, which is the size of the smallest logical operator. And as I mentioned before, the actual constructions of these things use particular mathematical tools, which are known as product constructions, which is kind of a way of taking simpler models and combining them to more complicated models in a systematic way. And these go into these arguments, but also they're just kind of interesting set of ideas for producing new models out of existing ones that can produce interesting physical models even in finite dimensions. Okay, so for the rest of the talk, I'll try to explain a little bit in more detail what I mean by all of this. And I'll start by reviewing the toric code again, but thinking of it in this language of Z2 gauge theory. So the toric code is this Hamiltonian up there. Again, we have a square lattice, qubits on edges, and there are two types of terms, one of Pauli X and the other one of Pauli Z type. First one associated to vertices, the other one associated to baguettes, which all completely different. And I can think of this as a paradigmatic example of quantum code, but it also shows up very naturally in physics, and it's shown up even before people called it code, as a particular point in the phase diagram of the system known as the Z2 gauge theory. So the Z2 gauge theory is this Hamiltonian below, which has a bunch of terms, but the basic idea is that there are two types of degrees of freedom. There are degrees of freedom living on vertices, and there are these degrees of freedom living on edges, which you can think of as kind of matter and gauge fields. So this is some very simplified model of the gauge theory from high energy physics, where you have kind of matter degrees of freedom coupled to gauge fields, and they're coupled to each other in some systematic way. and they obey something that is a generalization of Gauss's law that in electromagnetism, charges and electric fields are kind of tied to each other. Whenever there is a charge, it's a source of electric field. There's a similar constraint here that these two degrees of freedom are not infinite. And the phase diagram of this model has been studied a lot, and in particular, it has this interesting deconfined phase. And if you go to kind of the fixed point limit of the deconfined phase, you find yourself in the Doric code after some appropriate change of variables. You can get rid of your measure degrees of freedom and end up with a Hamiltonian just for these gauge fields, and it's exactly the Doric code. Okay, so how do you get something like this? The idea is that you can get these sort of gauge theories by starting with some system just for your measure degrees of freedom, which have some symmetries, and there's a notion of what people call gauging those symmetries, which turns a global symmetry to some local constraint. So here I could have just started with a two-dimensionalizing flow with a transverse field. So I have quantum spins on every vertex, they have some ZZ nearest neighbor interactions, and there's a transverse field. And one thing to emphasize here is that the first term in this model you can think of as a classical code. Like as I said, the 2D classicalized classical code, here I'm embedding it in some quantum Hilbert space and adding additional terms to it. But still, at the core of it, there's a classical code that I started with. And then there's kind of a systematic procedure of, and this is symmetric under flipping every single spin, which physically is a symmetry, but it comes from the kind of logical operators of the code that I started with. And now there is a systematic procedure of kind of starting with those symmetries and turning them into local constraints by adding these new degrees of freedom, these gauge fields, and coupling them to the original degrees of freedom in some particular way. And more intuitively, what this means is the following. So first of all, one thing is that this also means that there is some part of the phase diagram of the gauge theory which maps onto the phase diagram of the original model. So there's some duality relationship between those two. And the way to understand that duality is that I could use this Gauss law to get rid of my measure degrees of freedom. And if I do that, then I start with some measure degrees of freedom, couple them to gauge fields, but I can fix the measure degrees of freedom and end up with something for the gauge fields. So I end up with some mapping from measure degrees of freedom to gauge fields. And the kind of central relationship in that mapping is the one in brackets there, saying that the values of my gauge fields, they map onto the values on each link of the product of two spins in the original degrees of freedom. So what this means is that the configuration of the gauge fields is basically corresponding to the arrangement of the main balls in the original problem. If I start with some spin configuration, basically I could describe it rather than with the original spins, instead with the location of the main balls, which are misaligned spins. And that's what these new gauge degrees of freedom are. And importantly, the plaquette terms in the toric code, they correspond to the fact that there is a constraint that these domain balls have to form closed loops, which means that for every plaquette, if there is domain ball coming in, it has to go out. Okay? So now the key idea is that this whole construction of starting with some classical code, embedding it in a quantum system, and applying this gauging procedure to it, generalizes very nicely to all sorts of other LDPC codes, which are not the 2D IC. So the idea is that I have some classical code, which is described by some set of checks. So the checks will be the terms in my classical model, which is some product of spins along some designated sets of bits. And this code will have now just not a single symmetry, but many symmetries, one for each of the logical operators of the classical code. And as we saw, these local redundancies also played an important role in gauging. So we want to consider codes which have some analog of that there are some local constraints saying that there is some combination of checks that if I take their product, it always gives me +1, meaning that not all the terms in my original test code are independent. And the fact that these are redundancies will be important for kind of getting a quantum code where all terms compute with each other. Okay? And yeah, so this is mathematically this is described by these sets of maps. So I have 3 sets of objects, I have spins, I have checks, and I have these redundancies between the checks. And I have some maps which tell me which bit is part of which check is part of which redundancy. This is what these delta 2, delta 1 are. And if I apply them in sequence, I always get 0. They're just telling me that they're just encoding the fact that redundancies are indeed redundancies. All right? And so now, with this machinery at hand, you can go through the same sort of gating procedure. So start with some Hamiltonian, build out a classical code, and systematically introduce these new degrees of freedom, couple them to the previous ones, and you end up with some appropriate generalization of this Z2H theory, which will have some terms A and B, which are products of X and Z, Pauli matrices, and by construction they all commute with each other. So at some point in the phase diagram of this H theory, you have something which gives you a quantum LDPC code. So if I take J and gamma to be 0 in this, I have some Hamiltonian where every term commutes with each other, and I could the ground state manifold of that model gives me a quantum LDPC code. Okay, so this gives you a very kind of general relationship of going from classical LDPC codes, free local redundancies to quantum LDPC codes. Okay, and this is kind of building on previous work in the context of fractal basis, where people have come up with similar constructions. And yeah, so then we end up with some relationship that goes back and forth between classical codes with redundancies and quantum codes where you have 2 types of checks, X and Z checks, which commute with each other. And we can work out kind of in detail a dictionary of how these things map to each other in kind of full generality. And just to get some intuition, the most important part of this is that in the classical model, I can think of the generalization of domain codes. Start in the ground state, flip some spins, and ask what excitations are created, which of my curves get violated. That there be some configuration of domain walls, and those domain walls map onto what in the physics language are called Wilson loops, some product of my gauge fields along some closed loop. And on the other hand, the logical operators of the quantum code are also closed loops, just like in the Turing code, except the logical operators will be loops which are by construction non-contractible. They are not the boundary of some region, as opposed to the ones that I get to domain wall, which are by construction the boundary of that region where I fit my space. So one question is how to relate these two. I would like to somehow connect the properties of contractible loops to non-contractible ones. And a bit of intuition of how to do that is given by considering the 2D Ising model. So let's say that I again consider this question of what is the minimal energy cost of flipping a certain number of spins starting from the ground state. In the 2D Ising model, what I find is that initially that energy cost grows as square root of the number of spins I flip, which just comes from the fact that I'm flipping some region and the size of the boundary of the region is square root of the size of the volume. But what I find is that at a certain threshold, the square root growth stops and I get a flat plateau. And the reason for that is that if I make my number of spins that I flip large enough, then I can actually create a domain of flip spins that looks like that strip on the right-hand side. And the point of that strip is that once I created it, I can make it bigger without any extra energy cost by just pulling it apart. But the interesting thing about this from our perspective is that what happens in this transition is that the boundary goes from being a single contractible loop to a pair of non-contractible loops. So this transition in this function kind of tells me about what the non-contractible loops look like, which are the things that relate to the logical operators of the quantum code corresponding to that. So the height of this plateau is twice the code distance of the toric code, which is the quantum code related to this classical one. So using this gives us kind of a way of relating properties of contractible and non-contractible loops. And one feature here is that this flat plateau is kind of inherited from a lower dimensional 1D model. So once I created this strip, the problem becomes effectively one-dimensional. And this is where these product constructions I mentioned before come in, that the two-dimensionalizing model I can think of as kind of a product of two one-dimensionalizing models. So I think I'm running out of time, so maybe I don't go through the details. But the point is that I can build the 2D-izing model out of two 1D-izing models in a systematic way. And this feature of this plateau that you saw is kind of inherited from the fact that in the one-dimensionalizing model, domain balls can be moved apart without any error. And so what we see is basically that combining this gauge perspective of going between classical and quantum codes with the idea of using this product constructions gives us a way of relating contractible and non-contractible loops, which is a way of relating kind of how energy barriers in the classical model behave to the code distance of the corresponding quantum code. And as I mentioned in the beginning, these constructions of good codes also use versions of these product constructions, except they are more complicated versions that involve extra twists. But at least in one example, we can show that indeed the construction of a classical locally testable code and the construction of a good quantum LDPC code with large systems are related to each other by the same sort of gauge that I described. So yeah, I think I'm out of time, so I'll just give up this summary slide. And yeah, thanks for attention.
So you said in one example, there was this relationship. Is it an open question whether it generalizes, or what's the status there?
Yeah, so it's an open question, and to some extent that's what we're trying to get at. But there are so kind of this picture of arguing that they have to be the same through the fact that basically at some point, as I flip more spins, I should go through this transition where it's more favorable to have some small number of non-contractible loops. If that's always true, then it's generalized. And there are some arguments saying that it should, but there are some kind of alternatives I didn't want to.
So to say it a different way, for product constructions, we have proof that you can relate classical energy barriers to quantum code distance. There's one hole in the proof for balanced products, but then there are examples for balanced products where we show the gauge value that's this Mantel halogen construction. But there's still a hole in the proof that we're trying to build.
Okay. Also, I'll check back in a few weeks.
So this picture you're showing here of the behavior of this energy value versus number of flips, in this case it goes bad because the one of the factors in your construction has this freely movable expressions. So if you take a part of two good codes, you expect this to be a different power cascading?
Yes, what happens in that case is so if you look at what happens in a good classical code, what you find is that initially there is some actually linear growth of this energy barrier, but it doesn't go all the way at least in the sort of random constructions of good classical codes. Instead, at some point it sort of dips back. It actually dips back to some small order of value. And so that fact that you don't necessarily need this to be constant. You just basically wanted that there's some configurations that have low energy but include many specifics. That's kind of enough for your intention.
Any last question? If not, let's thank both of you.